We're going to talk about the causes of anthropogenic climate change. Anthropogenic means anthro, man, genic, to cause. So climate change caused by man. We'll know what is radiative forcing, what are the greenhouse gases, and we'll talk about the positive and negative feedback mechanisms. At the end of this video, make sure you know the difference between the greenhouse effect and the ozone hole. It's going to be tested on the final for sure. So in a nutshell, increased carbon dioxide and other heat-trapping greenhouse gases produced by our activities are resulting in an average global temperature increase. The results of this are many. There are going to be change in weather patterns, glacial melts, ocean acidification, and changes in biology. Global climate change was first predicted many years ago by Svante Arrhenius, where he recognized that the increase in carbon dioxide would cause global warming. However, he thought it would take many centuries because he didn't anticipate the exponential growth of our industrial activities. And he also thought it would be good. Of course, Svante lived in Sweden, where it's always cold. What we're looking at here is the intensity for different wavelengths of something that's hot. This would be 3,000 Kelvin, 4,000 Kelvin, 5,000 Kelvin. Oh, incidentally, the sun is around 5,600 Kelvin, so the sun is a little warmer than this. So when things are hot, they glow. And we see two effects. As they get hotter, they glow with greater intensity. Additionally, their emission peaks at higher and higher frequency or shorter and shorter wavelength. So these longer wavelengths are infrared and ultraviolet, and in between we have visible. And because the sun is a little hotter than 5,000 Kelvin, its greatest amount of radiation is in the visible, which we can see. However, cooler things like our bodies, for instance, radiate only in the infrared. And so if we look at the heat flows with the Earth, which we've studied before, light comes to us from a very hot body at very short wavelengths. However, the Earth is not near as warm, and we cool off with longer wavelengths in the infrared. These energy flows should be in balance if the Earth's temperature is not to change. So all of the energy we get via the sun in high frequency light, we should emit in low frequency light into space. If we were to prevent the Earth from radiating infrared light, then it would get warmer. As it got warmer, this infrared radiation would increase, bringing us into a new equilibrium, but at a higher temperature. And so we see this is exactly what happens. If we look at the emission spectrum of the sun, centered around the visible light, and the radiation spectrum from something cooler like the Earth, we peak in the infrared. The curves represent the spectra of the black body. The colored portions underneath represent the portion of that spectrum that can penetrate the Earth's atmosphere. And so what we see, water vapor, carbon dioxide, methane, nitrous oxide, all of these things absorb radiation, but they absorb much more in the infrared than they do in the visible. So essentially the sun's light can come through and warm up the Earth, but it's harder for us to cool off. This is only one small part of all the things that happen. The intensity of sunlight that penetrates the atmosphere is about 1,000 watts per meter squared, and some of it's reflected off of clouds, off the ground, and then the infrared light as well can be reflected back down from the atmosphere. The reflection from the atmosphere is the greenhouse effect, natural and man-made. We see that there are many energy flows from the incoming radiation of the sun and the outgoing radiation from the Earth. Again, these should be in balance. The amount of radiation coming in should equal the amount of radiation going out, which is this number plus this number. And the radiation is in terms of watts per meter squared. We see it's only 341 because this is the average over the whole planet, not just at noon, midday. the greenhouse effect has been in effect well before man's activities have caused it to increase. And without it, we would be very, very cold. So we're grateful for the greenhouse effect. But what's happened is recently we've been increasing it, and this is causing changes. The question is, do we want these changes or do we not want these changes? Instead of global warming, most people are now using global climate change. Because global warming, we've raised approximately a degree. That is not as significant as all of the other changes in weather patterns and biological activity that have resulted from this, directly or indirectly. So let's look at some of these greenhouse gases. CO2 in parts per million, methane in parts per billion, and the temperature as a function of years. This is thousands of years before 1850. We pick 1850 because that's when the Industrial Revolution started. And this is greatly extended. So this is 50,000 years here, and this is 100 years. So you can see there's an abrupt increase in these greenhouse gases in just the past 100 years. Where do they come from? Burning, agricultural, and industrial activity. And here's a big one too, deforestation. Because the forests are responsible for sequestering carbon dioxide. That is, during the day, they photosynthesize, they absorb carbon dioxide and turn it into wood, biomatter. Human contributions to greenhouse gases: carbon dioxide, methane, chlorofluorocarbons, those are refrigerants, water vapor, and nitrous oxide. For instance, in Arizona, because of all the fountains and lakes and watering of grass, it's now not an arid environment anymore. So that's one example of the water vapor that we're putting in the atmosphere. Sources of carbon dioxide almost perfectly reflect our energy use. A third transportation, a third goes to electricity, and a third goes to industrial and residential. We can look at these greenhouse gases. This is carbon dioxide equivalents. And so most of it comes from energy, carbon dioxide. However, cement, interestingly, is 4% of our greenhouse gas emissions through the production of cement. Deforestation is 20%. Agricultural soils, livestock and manure, cows fart and burp a whole lot. So we can look at the increase in carbon dioxide emissions over the years. At present, 2010, we're at about 35 gigatons of carbon dioxide, or just under 10 gigatons of carbon per year. If we divide by the 7 billion people on the planet, this is about 5 tons of CO2 per person on Earth, average. The United States is about 4 times that, about 20 tons. So we can look at the major contributors here, United States and China. And there's a couple ways to look at this. We might say China's the culprit. They're the largest increaser. They're growing so fast. So China has the greatest rate of change. At the same time, we can look at where we are and say, oh, well, China has slightly more GHG emissions than the United States, but it has about 4 times the population. So the United States per person is a much greater emitter. Furthermore, the area under this curve represents the total amount of carbon dioxide that the USA has emitted. And we can see when we look up in the atmosphere, the greatest portion of the carbon dioxide that exists there is because of our activities. So the United States has the greatest integrated amount. United States has 4 times per person the emissions of China, but China is increasing the fastest. It's worth noting that this 10 gigatons of carbon per year is small compared to the amount of carbon in plants, in the soil, and in the atmosphere. And there are huge turnovers of carbon dioxide in terms of photosynthesis, respiration, and decomposition. However, what we have going on is we are consistently adding a small amount of carbon every year, and it's accumulating. It's worth noting that it doesn't all go into the atmosphere. Some of it goes into the oceans. About 60 years ago, we began measuring carbon dioxide concentrations in the atmosphere, here in concentrations in part per million. And what we see is a sawtooth behavior that's very strange. It's an annual oscillation. And that's because there are more plants on land in the northern hemisphere. And so in the summer, they grow more leaves, pulling more carbon dioxide out of the atmosphere. In the winter, the leaves die and decompose, releasing more carbon dioxide. So these peaks correspond to the end of winter. However, these small oscillations ride on a consistently increasing curve. That's the result of human activities. So we can trace these back using ice core samples that you dig out of the ice, because when water freezes, it locks in at the atmospheric concentrations of the gases. So you can look at the abrupt rises in these 3 different greenhouse gases from ice core data. And we can look at over the 10,000 years, boom, over on the right, we have a different kind of measurement, radiative forcing. What is radiative forcing? It's the amount of effective heating that the gas does by absorbing and reflecting back the Earth's infrared radiation. And it's in watts per square meter. So for CO2, you get a positive 1.5 watts per square meter. Ozone, black carbon, because it absorbs light. We also see clouds and aerosols reflect the sun's rays, so they have a negative radiative forcing. It's worth noting that oscillations in the sun have had a very, very small effect. So when we add all these up, we get about 1.6 watts per square meter. What this means is if you took a 1.6 watt light bulb, like an LED light, and you put it every square meter over the whole surface of the Earth, it would warm the Earth up just a little bit. And that's what's going on. Feedback mechanisms are how the climate responds to change the climate even more. For instance, water vapor. The more you have water vapor, you warm up the land. This increases evaporation, and that gives you more water vapor, which gives you more warming, which gives you more water vapor. So that's a positive feedback mechanism because it propagates itself. The same with snow. As Arctic regions warm, they melt, and instead of having white, now you have a dark color. And this absorbs sunlight, which makes it warmer, which encourages more melting. For this reason, it's very important. We in San Luis Obispo have about 1 degree Fahrenheit increase in temperature, but in the Arctic regions, it's 5 degrees. So for clouds, it's interesting. They have both a positive and a negative feedback. The increased water vapor causes increased cloud cover. This increased cloud cover causes less warming because it reflects the sunlight. So that's a negative feedback mechanism. However, it also absorbs infrared radiation during the night, and this causes more warming. So which one of these two wins out? So you have people studying this and modeling the climate with computer models. Here we see the results of these different computer models. The width of the lines represents the uncertainty of what the model predicts, and this is the changes in temperature over the past 100 years. The black line represents the actual measured temperature increase. The blue line represents what the temperature should be if we just look at volcano and solar oscillations. And the red line includes anthropogenic sources of greenhouse gases. And we see there is no way that this blue line matches the data. So from the models, the scientific community has concluded that yes, human beings have caused a significant change in the temperature. So by comparing the model with actual observations, we can verify that our model is doing a good job. What do we do now with the model? Well, the model now can be used to predict what will happen in the future under different scenarios. And so here we have different scenarios of greenhouse gas concentrations: 400 parts per million, 600 parts per million, 850 parts per million. And this is the global surface warming as a function of the different centuries. And these different colors represent, again, different scenarios. This is the business as usual, and these are different mitigation strategies where society works together to limit the greenhouse gas emissions. Okay, so let's make sure we get this straight. we want to distinguish the greenhouse effect from the ozone hole.